Okay, so I gave back a couple of homework assignments. This is take 2. And we have an exam coming up, right, on Monday. So I hope we'll be able to start reviewing. I think we're just about through with the material on functions. If we don't get to starting to the review today, we'll at least for sure start reviewing Thursday for the exam on Monday. Now, so let's review a little bit what we did last time. Remember last time we learned these definitions: determinant, total, one-to-one, and onto. Okay? And now, what is it? Are all relations functions, or are all functions relations? Which one is it?
All functions are relations.
All functions are relations. There are some relations that are not functions. In order for a relation to be a function, what must it be? It must be something. It's actually up there. It must be determinate. Okay? And determinate means what? That's the vertical line test. Yes. You can't have two mappings from one point in the domain to two different points in the range. Okay? So, and then providing that it is determinate, then total, one-to-one, and onto all apply to functions. So total, one-to-one, and onto assume that the function is determinate. Okay? And total means what? What does total mean? It means all the points are used up in the domain. And onto means all the points are used up in the range. Okay? And one-to-one is kind of like a mirror image of determinate. What does one-to-one mean? That, instead of being the vertical line test, one-to-one is the what? Horizontal line test. And that means that if you can't have two different points in the range mapped to the same point, two different points in the domain mapped to the same point in the range. Okay? All right, so anyway, those were those definitions. Now let's, what we're going to take a look at first today is 14.38.1. And I'll have a handout for you on this. So let's take a look at 14.38.1. Now, we've already defined what total is in, let me see, what was the definition of total? Oh, here it is, 14.38. A function f on b cross c is total if b equals the domain of f. Right? So that's 14.38 is a definition. So do we prove 14.38, yes or no? Obviously not, because it's a definition. It's like an axiom. On the other hand, 14.38.1 is a theorem, total. And so this is like an alternate definition of total. But it's not a definition. We don't prove it. It's a theorem. And it says a function f on b cross c is total if, for an arbitrary element b, little b and big B, there exists a C such that f dot b equals C. All right?
Is there an arbitrary element C that's in C?
There must exist.
Oh, that's what it's saying.
That's what it's saying, is that if there exists, because this is the expression, there exists a C, range true, such that f dot b equals C. That is a Boolean. It's either true or false. Okay? And if that's true, then it's total, if there exists a C, such that f dot b equals C. Oh, for an arbitrary element b, little b and big B. Okay, now, I think you can kind of visually see why that is equivalent to what total was. Here, let's look at the picture for total again. Okay, that's in the upper right quadrant here. So total means all the elements are used in the domain, yes. Okay, and so what we're saying here is that with this alternate definition of total, and so by our definition, it's b equals domain.f. on the other hand, 14.38.1 says there exists a C. For an arbitrary element B in the domain, there exists a C in the range such that there's a mapping to that. Now,
What does the notation f dot b give you? In like in a practical example.
that's a really good example. Oh, that's good. So it's this. If this is A, B, C, and this is I, J, K, then if it's like this, yeah, then if this is B and this is C and this is F from B to C, this function F is defined to be from B to C, then an example of this is F dot C equals I.
Okay.
Now, actually, do we have an example of that notation? I think, yeah, here. Now, 14.37.1 actually, Ben. 14.37.1, that F dot B equals C and BFC are interchangeable notations. So, when we were doing this with relations, we would say CFI.
Okay.
All right, because this is the function note. If it's determinate and it's a function, you write it this way, but relation-wise, it's this. And these two things mean the same thing.
Does that mean the same as
This also means the same as what?
CI as an element?
Yes. Oh, that's good. This is a nice demo here. So this means C comma I is an element of F. Because what would F be? F would be the set of ordered pairs. In this example, what would the ordered pairs be?
AJ, BK, CI.
Yes. AJ, BK. My brackets are kind of squiggly here, sorry. CI. Yeah, so all of this is the same. All of this is just a notation. All right, so are we good? Now, the thing of it is that what you're going to do for me on Thursday is you're going to prove 14.38.1. Now, it's a rather involved proof. And so what I have for you here is a handout that has the proof. This is available on the web for those of you guys out there. And this is a proof with the hints, all right, and for you to fill in the actual proof steps, okay? So here's this. So you see alternate definition of total, a function f on B cross C is total if for an arbitrary element of B, and then we have that there exists a C, range true, f dot B equals C. So we start with f is total, and I've just given you, it's a little involved, so anyway, you can just use this paper and fill in. So that's one. And then, all right, and then last time we mentioned what it means, what a function composition is. And 14.39 is function composition, and we have, what we've been using so far with relations is we've been using the open circle for the relation product. Well, function composition is the same thing as the relation product, basically. Only thing is, the G and the F are switched. See? So, yeah, so that's the thing about it. And I think the reason we're doing this is because there's conventional math notation, and we want, and function composition is describe the relation product when you're dealing with functions. It's called function composition. And now the next theorem, and by the way, this is a definition, so do we prove 14.39? No. But now 14.40 is a theorem. Now look at what 14.40 says. It says, let G be a function from B to C, and F be a function from C to D, and let both of them be total. Now, what does that mean? That means if, let's do a little picture here. If this is, we have B, C, and D. So here's B, and here's C, and here's D, okay? So now suppose we have a bunch of things like this. Now, what does it mean? What does it mean for each one of these things to be total? All of these have something going from them. Okay, so let's just do just sort of in general. These are all going to one of these here, right? And if it's total from B to C, and if it's total from C to D, total means what? There's something going from one of these to here. So somehow to here, right? So as long as this, and going from here to here, this is G. So this is G, and G is going from B to C, and it says F is going from C to, so F is going from C to D, right? And now what does the theorem say? It says the composition, by the way we're going to say this is F composed G. Okay. All right, so that we said G times F, we say F composed G. All right, so then the composition F composed G of F and G is the total function defined by F composed G dot B equals F of G of B. All right, so it's just, what the composition is, it's just like the relation product. In other words, if you have all of this, this is equivalent to what? This is equivalent to a single one, and here if we hit B has 1, 2, 3, 4, 5. 1, 2, 3, 4, 5, and then D. And D had 3, right? 1, 2, 3. So, and this is total. All right? And so the composition, it's as if there is a single function. You know, the composition of those functions is a single function from B to D. See, so what we're saying is that F composed G. So here what we would have is we would have F composed G like this, okay? And what this theorem is saying is that F composed G of B, dot B, where little b is one of these, you can think of that as being one function from B to D. And it's equal to F of G of B. Now, and that particular theorem, the proof of that theorem is the second homework assignment. And I gave you, when I handed these out, you notice the second page. It was supplementary exercise S.18, and it's to prove 14.40. But instead of giving it all the hints, there's some hints on here as to how to proceed. Okay? So
composition and product are exactly the same.
They are exactly the same switched. That's it. So once you got the concept of what it means to have a relation product going from here to here, function composition is exactly the same concept. Only thing is you're dealing with, it's a little bit more restricted because functions are more restrictive than relations. Okay, so are we good? Okay, so that's your homework assignment for Thursday. And then what we'll have to do is I'll have to make sure, and if you hand those in, you better, actually, you know what? If you want those graded by Thursday, by our review session, you need to turn it in class, yeah. But if you don't, I'll grade it Thursday and you can have them available. I'll have them available for you on Friday. I mean, because I kind of doubt that in fact, you could even hand it in at the review session if you want. Maybe let's just plan on that. Why don't we just plan on having me get these back to you on Friday, okay? All right. Now, so the only thing we have left to do now is a few more things about functions. Namely, we need to understand the concept of the inverse. Now, we actually reviewed, I think we used function inverse last semester, did we not? Do you remember we had a theorem? Didn't we prove? In fact, didn't you have to prove a theorem that said if F inverse exists? Do you remember we did that? Do you guys remember that from last semester?
Did we use these same numbers?
No. We used the concept of an inverse function. Didn't you have to memorize a proof that said that provided F inverse exists? Wasn't that one of those? Here, let's look. Here it is, change of dummy. Do you remember, here, let's look here. 8.22, change of dummy. Do you remember proving this? provided y does not occur in R and P and f has an inverse,
I do remember that.
there exists, star x, range R, body P equals star y, range R with x replaced by f dot y and body P with x replaced by f dot y. That was changed, and I think you proved this.
I think you gave us the.
I think, yes, and you fill it, but I think you had to prove that. I think this was so important. I think I said this is one of the questions on an exam. And so we used this concept that f had an inverse. And remember, in doing this, we said f. What did we say? We said f dot x equals y equivales what? If f has an inverse, what does that equivalent? Going the other way, what does
f dot y equals x?
Well, not f dot y, but what? F inverse dot y equals x. I think we used this. I think this is one of the steps in that proof. Well, that was a long time ago. But anyway, now that it's recorded, we could actually go back and access it. And so now let's take a look at the concept of an inverse. So 14.41, these are the definitions that we've gone over before, onto one-to-one. And 14.42 introduces the concept of an inverse. So let f be a total function. Okay, so total, all the ones in the domain are used. A total function, and let f minus 1 be its relational inverse. Now, do you remember what relational inverse means? What was the relational inverse? If A, B is an element of rho, equivals what? BA is an element of rho inverse. All right? Okay? So we know what this is for relations. It's the same thing for a function. Okay? So here it says, let f be a total function and let f minus 1 be its relational inverse. Then f inverse is a function, i.e. is determinate, if and only if f is 1-to-1. So that's part A of the theorem. And part B of the theorem is, and f inverse is total if and only if f is onto. Now what the heck does, I think we should be able to understand this. We're not going to prove it. We're not going to prove, these are theorems. We're not going to prove them. I wish we had more time. This was really good math. And if we had more time, if we weren't so rushed, we would stop, we would be real thorough and actually learn how to prove these. But I think you can see what the idea is. Let's take a look at 14.42. 14.42. This idea, let's call this idea. Okay, so first of all, let's take a look at the idea of A. Now, what does A say? It says, let f be a total function. Okay, so if it's total, then that means that let's say that we have something like this. Let's just do it like this. Suppose this is B and this is C. And let's just say that it's like this. And the mapping goes like this. Okay? Now, is this total?
Yes. If it's B to C, it is total.
And is it 1-to-1?
No.
Okay, so f is total. So here let's say f is total. F is not 1-to-1, right? So now what about the inverse function? Can you tell, is the inverse function, is the inverse relation,
The inverse relation is not a function.
Yeah, it's not a function, right? Because the inverse would look like this. The inverse is not determinate because what you would have is this would go, you would have two, you'd have going from here to here. So what we're saying is so here f inverse is not determinate. So on the other hand, if this is 1-to-1, then can you see that the inverse will be determinate?
Yes.
All right? Are you with me on that? So f inverse is not determinate, so therefore f inverse is not a function. This function does not have an inverse. Okay? So here, let's write this 3 different ways. F inverse is not a function. The relational inverse is not a function. Okay? So what we say then is that f does not have an inverse.
Okay. So we only consider it to have an inverse if the inverse is a function.
Yeah, well, it does not have an inverse function.
Oh, there you go.
See what I mean? Because the inverse isn't a function, so it doesn't have an inverse function.
It is the inverse relation.
It is the inverse relation, but we don't have an inverse function. We're talking about inverses of total functions. And so, yeah, okay, so that's the idea. And you could prove it, but I think you can see it once you understand the definitions here. Okay? And now how about the other one? Can we see the board over here?
Oh, yeah.
Okay. Now, how about so that's part A. How about part B? Okay. What does B say? F inverse is total if and only if f is onto. Okay, so here let's have B and C be here, and let's do this. Let's have B have this 1 and C have these 2 like this. And let's say that B, the mapping from B to C is like this. Okay. So now the question is B onto? Is F, if this is F, is F onto?
No.
Yeah, F, so here, F is not onto. Because in order for it to be onto, all of these have to be used up. Okay? So F is not onto, so therefore, what does that say about the inverse relation? So the inverse relation, it's going this way, right? Okay. So now what can we say? Because F is not onto, then what about F inverse? Yeah, but what is it not? If F is not onto, then F inverse is what? Is not what? F inverse is not total. Because all these aren't being used in the mapping and going from here to here. So I think if you see the picture, you can see that F inverse is total if and only if F is onto. And it works the other way around. In other words, if F would be onto, then F inverse would be total. All right? So these are just diagrams illustrating what's, we should be able to see that 14.42 is in fact the case. All right, and now we want to do one more thing. I want to give you one more example, and this is 14.43. We want to talk about the concept of a left inverse and a right inverse. And then I want to give you an example of how this works. So let's take a look at definition 14.43. It's the concept of inverses. Now, what we mean by a left inverse and a right inverse is depending on if the what is it when like if you have an algebra, A times B is B times A, what property is that? That's symmetric, right? Also called commutative. Well, the inverse has to do with that. If something can be a left inverse but not a right inverse, or it could be a right inverse and not a left inverse. Okay, so it's actually possible if the property is not if it's not symmetric, then something that's a left inverse might not be a right inverse. If it is both of them, then it is an inverse. So function and these are, by the way, these are definitions. We're not proving these. So the definition, so if it's both a left inverse and a right inverse, then it is an inverse. Okay, so here we have a left inverse of f is a function g from c to b such that g, now how do we say this?
F compose G?
Yeah, oh, this is g compose f.
Oh, the top one. I'm sorry.
Oh yeah, sorry. So g compose f is the identity
Okay.
of b, and here a right inverse of f is a function g from c to b such that f compose g. So now you see, which one is the inverse? The g is the inverse, right? So g is on the right of f, okay? And here g is the inverse. G is on the left of f, okay? So if f compose g is I sub c, and then function g is an inverse of f if it is both a left inverse and a right inverse. Now what I want to do, these are definitions, so we can't prove them, but I want to give you an example of 14.43. All right? So now here's what we're going to do. We're going to use the two functions that we're going to illustrate this with are neg and abs. And so here's what we're going to do. Here's our C, and our C is going to be, we're going to have three elements in C. Okay, 0, 1, and 2. And then here's our B, and our B is going to have 2, 1, 0, negative 1, and negative 2. So this is 2, 1, 0, negative 1, negative 2. All right? And this is going to be neg. We're going to have the neg function, and the neg function is going to go from C to B. All right? And then, okay, so actually before we go any further, let's verify that this is in fact a function. Let's do the mapping and verify that it is in fact a function. So what do you suppose the neg function does? So neg dot 2, what do you suppose neg stands for? It's to negate. It negates.
So 2 would go to negative.
So here 2 would go to the negative 2, 1 would go to the negative 1,
And that is all.
and 0 would go to the 0.
Oh.
Yeah, because 0 is neither positive nor negative, so if you take if you negate 0, you get 0. All right. Now let's describe all of let's describe this neg. First of all, let's do all four. First of all, is it a function? In other words, is it determinate? Oh, maybe not. I hear a deafening silence.
It is determinate.
It is determinate. Now, how do you know that it's determinate? Because there's not what?
More than 2 going off the one domain.
Yeah, we don't have, yeah, okay, so it is determinate, okay, and then is it total?
Yes.
It is total because all these are used, right? Is it onto?
No.
It's not onto because we have some here that don't have a mapping to them. What was the other one?
1 to 1.
Is it 1 to 1?
Yes.
It is 1 to 1 because we don't have two things going, two different, okay? But it's a legitimate function. Are you with me? Are you with me, sports fans?
Yes, yes.
Okay, so now let's take from B to C. Now let's have another function, and for B here we're going to do 2, 1, 0, negative 1, negative 2. So this is 2, 1, 0, negative 1, negative 2, and C is here. 2, 1, 0, and so here's our C. Okay? And now this function is going to be, you guys know absolute value?
Yes.
Okay, so we're going to call it the abs function. We'll make sure it's function, okay? Abs from B to C. Okay? And how does the absolute value function work? It maps what to what?
A number 2, it's absolute value.
Yeah, so 2 would map to
2 to 2.
2 to 2,
1 to 1.
1 to 1,
0 to 0.
0 to 0,
Negative 1 to 1.
negative 1 to 1,
And negative 2 to 2.
negative 2 to 2. Now let's do the 4 properties of this.
It is.
Is it determinate?
Yes.
Why is that? Because you don't have one of these going to 2 different ones over here. Is it total? It is, because all of these are done, right? Okay. Is it onto?
Yes.
This one's onto, because these are all used. Okay. And is it 1-to-1?
Absolutely not.
Absolutely not, because we have these 2 different ones going to the same one over here. Okay, so does everybody, I didn't write all that down, but you got it? Are we good? Okay, so let's let little b, because here we're doing compose, but compose is the same thing as product the other way around, right? Okay, so let's let little b, this is kind of, be in C. Okay, so in other words, a natural number.
Okay.
I mean, if you notice that the C was 0, 1, 2, right? So those are natural numbers. These are finite ones, but anyway. If it's a natural number, it would work if it went on up, right? Okay, so let little b be in C. Let that be. Now here's my question, you guys. What is apps compose neg dot b? What is apps compose neg dot b?
Well, that's the same as abs neg dot b, right?
Yeah, this equals by what theorem? What was the
I
compose
think it's 4.
abs? There was a,
Oh, I'll get it.
here, let's show it actually on the video. This is the one you're going to prove actually, right? 1440. Okay, so this equals by 1440. This equals by 1440 abs, parentheses, neg dot b. Is that right? But this equals by now. Now here's the question. This equals by the definition of neg. We're using a little math here now. So neg b, so this is abs. So this is just, negative b, right? Are you with me? Okay. But what does this equal? What do we know about the value of, what do we know about b?
That equals abs of negative b.
Little b is a natural number. So what's the abs of negative b?
I don't know how to say it. I know what the answer is.
Yeah, well, it's easy to say if you know what the answer is.
I can give you the literal answer. I can tell you the numbers. Right?
Well, what's the abs of negative, if b is a natural number, okay, which we over here, look.
Yeah, 0, 1, 2.
Yeah, 0, 1, 2. So what's the abs of, what's the abs of negative 0?
0.
What's the abs of negative 1?
1.
What's the abs of negative 2?
2.
So what's the abs of negative b?
Oh.
Okay, so this equals by the fact that, this is the definition of abs. Here, you see what I'm saying? So this is
very, very simple.
definition of abs because b is greater than 0. Because b is greater than or equal to 0. This is b. Are you with me?
Yes.
All right. So look. So what did we just demonstrate by this sequence? What are we saying? We are saying what? That abs. We are saying abs compose neg
Left inverse.
equals. Well, yeah. We're saying abs compose neg dot b equals b.
Right. Yeah.
So therefore, what is abs?
Composed.
Compose neg?
It's left inverse.
No, no, what does it equal? Ah, this is, yeah, now if you can get this one out of the, yeah.
The identity. Oh, the identity.
Yes, it's the identity, because the identity, you remember, what is the characteristic of an identity? You know, here, what do we know about the identity? What do we know about,
Reflexive. Right?
yeah, it's, yeah, exactly, yeah. So what we know about the identity is that it has all, the ordered pairs are all the equal, they're all equal. So therefore, what we're saying is that abs,
Was it wrong that I said that?
no, it was absolutely right. In fact, that's what I'm going to write down right now. So abs compose neg equals I sub, now which, is it I sub
I sub C.
B, or is it I sub C, or is it I sub B?
I sub C.
It is I sub C. All right, now you tell me now then, which one is the invert? Which one is the, so what is neg? According to this definition, what is neg?
This number. Neg is.
Oh, here, not according to this definition. But, whoops. Here.
Yeah. Neg is G.
So neg is the what? In this example, of? Yes, of abs. Okay, so here what we're saying is that neg is the right inverse of abs. All right, so that finishes the example, and that finishes all of our discussion of functions, and it's too bad we don't have more time to do more proofs, but we'll end it right there. And the exam then on Monday goes up to 1443, and then we're done.
Excellent.
And do you want to leave 5 minutes early?
Yes.
All right, good deal. You owe me 5 minutes. No, I think the bank, I think I've already overdrawn the bank. I think I've kept you enough. So this is a little bit of payback. Okay, good deal. See you on Thursday.